Good afternoon. I'm Régis Somla from Blue Morpho. I'm CTO of Blue Morpho. And I thank you all for your interest into our activity in the frame of the EnSO project. This webinar is funded by the EnSO project. So in this first webinar in a series of three, I would like to welcome today our speakers. Our first speaker today will be Anne Labouret. Anne is CEO of SOLEMS. So good afternoon, Anne.
Hello, good morning.
And our second speaker will be Mrs. Janina Paris, who is a development engineer for MAHLE. So good afternoon, Janina.
Thank you, Régis. Good afternoon, everybody.
And our third speaker for today will be Mr. Jérémie Guillen, who is technology manager at ENERBEE. And good afternoon, Jérémie.
Good afternoon, Régis. Hi to everyone.
So today, the topic is about energy harvesting, but let's first talk a little bit about the EnSO project. So, EnSO, it's a European consortium, a huge European consortium. It stands for Energy for Smart Objects. We are a team of 33 partners and 5 sub-parties over 8 different countries, and with a total investment which is in the range of 82 million euros and supported by the Excel project. You have here all the partners, so I will not go in the details of all the partners, but you see that we have the whole supply chain from integrated device manufacturers, end users, people who are more involved into the material, so maybe at the lower end of the value chain, and also some academics and research organizations. And for the integrated device manufacturers, we have our 3 guests today: SOLEMS, MAHLE, and ENERBEE. So EnSO, what it is about? The objective of EnSO is to work on the autonomy of smart objects. As you know, IoT is on time to market. It's speeding up really fast at the moment. And there's more and more issues in managing the power of smart devices. So smart devices is composed of a sensor, data processing unit, and data transmission. EnSO doesn't deal with this. Even though we are working on some demonstrators, the key development in EnSO is about what we have called the AMAS. The AMAS is an autonomous micro energy source. And this is a device where you integrate all the functions that will deliver the power to your sensors, data processing, and data transmission. So you have energy harvesters. You also have the possibility to perform wireless charging, and also power conditioners and a battery, rechargeable micro battery. These devices can deliver from 0.1 to 100 milliwatts, and with a current which is typically between 1 and 20 milliamp hours. This is for the micro battery. In fact, today we are going to discuss the energy harvesting. This will be the first webinar that we will broadcast in EnSO. And the next webinar will be about power conditioner, and then on the micro battery. So we have a number of demonstrators running. Some demonstrators deal with smart health. Some are dealing with smart mobility and what we have called smart society. And you see that we go from the energy harvester to the power management, to the energy storage, up to the use case. So there will be a dedicated webinar where we will disclose and explain all the use case and explain the performances of each demonstrator. This last webinar will be broadcast probably in January. But for today, we want to talk about energy harvesting. So I will hand over the control to Mrs. Anne Labouret. So Anne, you will be soon live. So Anne, for the beginning, can you give us a few words about SOLEMS, what you do, and who you are?
Of course, thank you, Regis. So SOLEMS is basically a French SME that is producing small devices for PV cells and modules, so all in a small sizing. We both design and manufacture ourselves these components. We are located in Paris, and so our products are small indoor PV cells, modules, and light sensors also. And our technology is amorphous silicon, which has the advantage of being very easy to produce in small sizes, various voltages, and thin glass, and so on. So my presentation will be more focused on the design, as this is the subject today. But you can see already on this picture one of our machines that producing amorphous silicon on the bottom of this page. So now if I can click to the next slide, you will see a little bit more about what I'm going to say. The slide is not coming. Yes, it is there. So PV harvesting, when you start the reflection of a design where you need PV solar cell for your harvesting of a system or a smart device, the first question you have to ask is how much light is available for my application, for my use case. This is the main thing you have to do first. Because if you go to indoor artificial light, as I'm saying on this slide, you will meet a resource of light that will be between 0 and 3000 lux. Example, in an office, you're working with about 200 lux. In a corridor, it can go down to 50 lux. So it is a very low level of input energy. The second condition of outdoor sunlight, you see as much more light available. So you can have from 5,000 to 100,000 lux. So it makes two very different kind of applications. First case, you are indoor, and then you can use microamps for IoT, for displays, for watches, as I can see some examples on the top of this slide. The first one on top, on the right, is a thermometer that is dealing with heating in a house and communicating with the central heating system. And the second is, well, I cannot go in all the details, but you see the kind of examples. And if you are outdoor, of course, you will have much more energy available. And you can imagine to use milliamps or sometimes amperes for also remote applications like metering, telecommunications, and things like that. So it is very basic, but it is very important to consider these two kind of applications, because of course the amount of energy will not be the same at all. Then maybe I will focus on the indoor case, and I will show you a little more. And of course, because solar energy is not permanent, you will need probably recharging. In the EnSO project, we are focusing on micro batteries. You can see on the picture. And this is very important to know that it allows you to make very small devices because of the volume of the micro battery. For the other kind of systems, you can also use nickel hydride or lithium batteries of other kind of capacities. Supercapacitor can also be used sometimes if you have enough voltage range, because the supercapacitor will need various voltages. But you can also imagine sometimes some hybrid systems where the power can be supplied in parallel with a primary battery and with a solar cell. And in some very individual, some very specific cases, you can also use no storage at all, like in a calculator where you have just a small capacitor to start the systems. So you have different solutions for the storage of the energy. Now I'm going to tell you a little more about how to design a solar cell in order to be able to know which kind of solar cell can be used for your system. Yes. So the first thing you have to do is first you have to draw your consumption profile, which will tell you how much current you will need through the time. And because we are speaking of a very rare energy, especially indoor, if you have seen what I said at the beginning, you have to really think about the real needs. This is a very important stage of the development. You have to consider your needs and really think about what is a real time for me. Is it necessary to make a measurement every second, or is it enough if I make a measurement every hour? It would make a very big difference in the consumption. So the third step will be, after you think about how to reduce your needs, you will then reduce your consumptions, either by lowering the currents or the durations. And then you will calculate on a day, because this is the natural unit for a solar cell. You will estimate on one day what's the consumption of your system, and you will evaluate also your light intensity scenario. Try to see where is the system located. Is it indoor? Is it in an office? Is it in a shop? Is it outside? And so on. So this is something we can help with, of course, in SOLEMS. So we can help you with this kind of reflection or design. And then you can, with these two elements, scenario of light intensity and scenario of consumption, you can evaluate the feasibility with our existing solar cells that you can find on the website, on the link that is shown there. And of course, if you need help, we will help you. And of course, if the solar cell you need is not on the list, we will make it for you. Because SOLEMS has an advantage, is making a lot of specific solar cells, because our tool is very flexible in terms of how many lines we put on a component, what's the size. This is completely open. So I will show now an example where you can see how to do practically. Let's say we have a system that's consuming 3 volts with 1.5 microamp in the idle mode and 50 milliamps 100 millisecond every hour. It's just an example. I mean, it's just to show you kind of system that would communicate sometimes every hour with another component. So we can calculate the consumption of this system, and you will get about 70 microamps per hour per day. Then next step, as I said, is optimization. Let's say that you optimize the system and get a sleep mode that's going to be smaller, like 100 picoamps during the night, and you have the possibility to reduce the consumption to 20 milliamps, let's say, instead of 50 milliamps. It is just an example. Then maybe you can realize that it's not so difficult to reduce the consumption by a factor 3, because the result is 25 micro per hour per day. Then in the light scenario, you will consider, for instance, in an office, that you have 200 lux, 8 hours per day. Then what is very clear is that the need is that roughly you will need 3 microamps for the solar cell, because you need 25 microamps per day divided by 8 hours. So you need 3 microamps. And if you look at the file, I was quoting on the last slide, this file here, you can consider that, for instance, on this particular case, the solar cell 10, 48, 12 would be okay for this kind of need. Then this solar cell is 48 by 12 with 10 sub-cells. The number of sub-cells on a solar cell is determined by the voltage. So here I detailed the current, but it's also necessary to consider the voltage. And here, because we need 3 volts, we'll also need 10 sub-cells in that particular case, which you will see if you look at the slide. I have no time to show you now, but you can see, if you look at this slide, all the possibilities of our solar cells in various sizes and voltages. So I will conclude by a short summary of what SOLEMS can do for you. We make solar cells that are particularly excellent under low illumination. That's why we enter the applications of IoT. Because amorphous silicon, sorry, it goes too fast. So amorphous silicon has a very particular, sorry for the slides to go fast, has a very particular properties in low illumination. As I said before, we can make various thicknesses, various sizes and voltages. We also perform, on the second kind of products, we also perform weatherproof little modules for various applications. We supply also expertise and design, simulation, prototypes, and we incorporated many R&D programs in solar energy like EnSO. Well, that's what I wanted to say today. Final slide, you will find all the contacts, my own contact at the bottom, CEO, and a little picture showing that we really make all these solar cells here in France, in Palaiseau, France, near Paris. So thank you for listening, and then I think we will be open to more questions if necessary.
Thank you very much. So indeed, the floor will be open to questions at the end of the presentation. So thank you, Anne. And the time for me to switch to and we will move on with the next speaker. So our next speaker today is Mrs. Janina Paris. So good afternoon, Janina, again. So I will give you now the control on the slides, and you will have the possibility to introduce us to thermoelectricity. This is a kind of very different way to harvest energy, and which is which requires a lot of material science and a lot of know-how. So Janina, the floor is yours.
Okay, thank you, Regis. So hello again, my name is Janina Paris and I'm working for MAHLE Thermoelektronik, which belongs to the MAHLE group. It's a German company that is traditionally developing and producing engine components. But in MAHLE Thermoelektronik, we are developing and manufacturing thermoelectric systems, which means that we are using thermal gradients to power, for example, wireless sensor systems. In the EnSO project, we are also working in the energy harvesting work package. So, okay. So probably one of your first questions is what is possible when using thermoelectric harvesting to power a certain application? Or the picture on the left shows you an example of how a typical thermoelectric harvester was used in an IoT application. So this module was mounted on a tube, and it was used in an air conditioning application, which was indoor. With, for example, a temperature difference of 10 Kelvin between the hot side and the ambient temperature, a power output of 1 milliwatt is reached. You can see this in the table. And however, the higher the temperature difference, the higher the power output. And this relationship is even quadratic, as you can see in the diagram with the red line. So why would it be beneficial for you to use such a system? Often power supply for wireless sensor applications is a key limiting factor for broad adoption. And this is why the utilization of such a reliable thermal harvester can save significant cost and reduce maintenance, for example, by avoiding battery changes. How does it work? Generating electrical power from heat. So we are making use of the thermoelectric effect. It's also called the Seebeck effect. And what you need is a temperature difference between the hot side and the cold side, so that consequently a heat flow can go through the material. In addition to that, you need two different thermoelectric materials which are connected in series. As you can see in the picture, there is an N-type material and an P-type material. So like this, heat is directly converted into electricity. And because there are no moving parts, maintenance is very low. Some of you may already know standard bulky Peltier elements that can be used as a thermoelectric harvester. So these modules contain a lot of thermoelectric material and they require a high level of manual work. You can see this on the left side. And this amount of material is why they are expensive. So thin film concepts overcome this problem because less material is needed. And in the concept shown in the middle picture, however, the effective temperature difference is quite small because, as you can see, the hot side is very close to the cold side and the high heat flux is required. So in our approach, we are also using a thin film technology, but the design of the element allows an in-plane heat flux. As a result, a higher temperature difference is provided and a higher output is achieved. On the right side, you can also see a picture of our elements. In addition, our approach enables the soldering of all internal thermal interfaces and thus an efficient and simple production of different subsystems as possible. As you can in the next slide. Because in this way, there are different options to use various types of heat sources and cold sites, and of course combinations between these different types. So a flexible adaptation to the customer's needs is possible, as there is flexibility, sorry, in terms of, for example, the cooling body and size and material. It could be, for example, made of copper or aluminum. And in addition to that, there is flexibility in terms of the amount of our thermoelectric material. Flexibility in terms of small to large area harvesting, depending on the heat source intensity that is available. And we can also influence the voltage to current ratio. So now the question is how to adapt our technology to your application. Regarding this, three main aspects have to be considered. First, the mechanical connection, then thermal design, and in the end, the electrical configuration. So concerning the mechanical connection, it is important to identify the installation space conditions. So what size of space is available and what kind of heat source is available. Is it, for example, a tube or is it a flat surface? A simple interfacing towards the hot and the cold side is essential for fast assembly, but in addition to that, the interface has to be also thermally conductive. So because relating to the thermal design, we have to discuss the available temperature difference and the heat flow. A good thermal connection helps to make the best possible use of the available heat flow because we can avoid high thermal resistances outside the thermoelectric material. So as a result, the highest possible temperature difference at the thermoelectric material can be provided. In addition to this, the amount of the thermoelectric material can be adjusted to the intensity of the heat source, so we can reduce or, for example, the material when the intensity of the heat source is high enough. So do not worry about the formulas that are shown here. These formulas show the relationship between the heat flow, the temperature difference, and the thermal resistance. But we will help you with that when we have to calculate your application. So the last main aspect mentioned here is the electrical adaptation. In this context, the energy needed by your application is the key topic. For example, by increasing or decreasing the amount of our thermoelectric material, we can customize the output, matching the needs of your application. But as I already mentioned regarding the thermal design, this will also affect the thermal adaptation. So in addition to that, I have to mention that the output of the output voltages of a thermoelectric system are typically rather low, in the range of millivolts. And to achieve, for example, 3 or 5 volts, a step-up DC-DC converter can be used. These electronics are developed by some other partners inside the EnSO project. And I think Regis will mention this later. Basically, it is important that your applications are as efficient as possible and have low energy consumptions, because only in this way a battery replacement can be delayed for a long time or even completely avoided by using, for example, thermoelectric energy harvesting. So, thank you.
Thank you very much. So yes, indeed, this is a very interesting technology, and I have tons of questions. We'll ask them a little bit later, but for now, we want to welcome Mr. Jérémie Guillen, who is Technology Manager at ENERBEE. So, Jérémie, I will leave you the floor. You have now the control of the slide.
Okay, perfect, with pleasure. Hi to everyone again. So I will introduce ENERBEE. So ENERBEE is a startup company that was founded in 2014, based on the Grenoble INP and CEA researchers. So we are 18 people, technology experts and business professional, and we came from initial funding and venture financing. So what do? We have a technology which is based on the movement. So we harvest energy based on movement, and with this we develop and industrialize fully autonomous products for the IoT markets. I will jump directly to the next slide. So we have 11 patent families in our technologies, and we won several awards from the French Ministry and Industry Ministry. So what is the IoT fundamental power challenge? Is that there will be many devices, so more than 20 billion devices are in the IoT device, and how to power it after 2020. So to enable this, wires are not always appropriate because we want mobile applications, and batteries may not be suitable because they are not sustainable or they do not fit to the application, and plus they are expensive to maintain. So ENERBEE value proposition is to provide fully autonomous products that give access to sensor data without batteries nor wires. So ENERBEE technology, how does it work? First, we take an energy source that comes from a mechanical motion, an air motion, a gas motion, or water motion. Then we have an ENERBEE generator. We'll look in detail later on. This generator converts a motion into energy, electrical energy. Then we can have a power management to manage the discharge of these energy peaks that are generated, and then store it if needed. Then provide an electrical generation to sensors. So we can have temperature, humidity sensors, as well as pressure sensing, airflow sensing, and mainly CO2 sensing and VOC sensing as well. And then take this data, record it, and send it wirelessly. Now let's look at the bottom of the slide what is inside our micro generator. So we have a specific technology where we have two parts. You see a ring, which is a magnetic ring, an assembly of magnets. When you have a flow of gas, of an airflow, for instance, we use a turbine to make it rotate. So you see the turbine on the right. So that makes the magnetic ring rotates. And this magnetic ring is based on 8-magnet assembly, is generating a vibrating magnetic field as it is turning. So then inside the magnetic ring, you see the core part of a generator, which is two piezo and in the middle a metal. So the role of the metal is a specific metal which is magnetostrictive. That means that when you have a magnetic field which varies, there will be deformation and strain in the metal disc. Then we glue to the metal disc some ceramics, so the glue transmits the strain from the metal to stress to the piezo. And as it is well known, in the piezo, it charges. So when it experiences some stress, then it gives charges. So that's the flow of the mechanism. Now, let's see what can I expect from this energy harvesting, which is motion-based. So we harvest about 100 microjoule every 90-degree rotation, whatever the speed. So that makes 1 to 10 milliwatt power range. So the size of our device are 25 millimeter in diameter and 5 millimeter in height. And I will jump directly to the rest to see product example and technology assets mainly. So the technology assets we have is, if we compare in a real case when our device is placed in an airflow, so in a pipe in a ventilation unit, for instance, we see on the left a graph mentioning the generated power versus the airflow in the pipe. So when we use a standard motor at low airflow, we do not generate any power, and we need a few tenths of meters cube per hour to generate some power. At the difference of our piezomagnetic generator that generates from low airflow a small power of 1 milliwatts, and then increases as the quantity of movement increases. So that's the let's say a big difference between motor and a piezomagnetic generator, so that it starts at low airflow. And the second thing, if we compare this with, for instance, batteries are often more expensive than our technology, because if we want to replace our technology with something with battery, we need to replace it often, and this price of maintenance in building is not permitted. Is prohibited price, and therefore that makes or let's say that our technology gives the best combination between cost, power, lifetime, operating hour, and our environment. So if we look then how to design a system, we need to think about the application and the environment which generates movement. About the generator, we need to think what kind of generator we use. Do we need our own technology, or vibration, heat, light, as mentioned by SOLEMS and MAHLE? Microwave, motion, electric potential difference. There are many other sources that can be investigated as well. Then, what kind of type of generation do we need? Current generator, or voltage generator, or something else? Then about the storage, what do we need to store? Do we need to overproduce and to store it for a long time in case the device stops? So the use case definition here is the key. And then finally, about the sensors, we need to see what kind of sensors are needed, and what is their current consumptions for each of the sensor. And finally, for the data transmission, the protocol has an impact. So for instance, how far do you want to send the data? Because it can represent more than 50% of the power used. So now, if I go into a flow, so how to design this product based on an energy harvesting system. So, as the other partner said, the first thing is to identify the use case and application. what is the criticity? Is there any security related? Do we need a backup, for instance? Do we need to have a double design? What is the lifetime of the application? And then what is the cost of ownership that is needed in the application? So do you prefer to have battery and battery replacement, or do you need something that is used all over the time during the full lifetime? So that's an important criteria. Then second step, do you need an energy source which is stable and available continuously, or can it stop? So it has an impact on the storage, because if you need to have a device which is constantly up, it's not the same story as it can go off and on. Then the third point is what would be the electrical model of the harvester? So we talk about this. Is it a current generator or voltage generator? So that has an impact on the electronics inside. And then the last topic is to define the power management strategy. We have to set, and we have a lot of patents on this, to know if we need to consume constantly the energy provided, or if we consume on demand, which implies a local buffer, storage, supercapacitor, and so on. And finally, the last, but not the least, the implement and test. So here, it's important to have many design loops and to test the lifetime and reliability before to ensure the lifetime is a good one and fits well with the application. Finally, we'll conclude with examples of products developed by ENERBEE. So we developed indoor air quality measurement and control devices. Some devices that are controlling the ventilation units, or some devices that distribute the airflow within a building, for instance. And in the last slide, some industrial IoT deployments of these autonomous devices. So some devices that are made for retrofitting machine monitoring to gain information on the machine use and process parameters during the processing, or some mobility device, for instance, to know the seat occupancy in the trains, and finally to know the bed occupancy in the health in the hospitals. So that's all product examples that were developed by ENERBEE. So if you have any questions, feel free to get back to me. Thanks.
Thank you very much, Jeremy, for this very interesting presentation indeed. So now we're going to open the floor to a few questions. So while we're going to wait for a few questions to appear on the chat box, maybe I can start with maybe for Anne from Labouret from SOLEMS. You didn't speak too much about the flexible substrates. What can you do about? What can you explain about these photovoltaic devices or flexible substrates?
Yes, thank you, Regis, for the question. The thing is, in EnSO, we are, as you say, we are developing flexible solar cells. Of course, some people have already seen some flexible cells on various substrates. The problem we are meeting is that it is a sort of compromise between lifetime and flexibility, because most of the substrates that are used for flexible solar cells are plastic, and plastic is not the best for industrial applications or long-term applications, because of its durability is not really excellent. So we decided in EnSO to go to flexible glass. And this is on the way, but it's not so easy. And the technology is nearly ready. But I didn't talk about it because we are at the moment having a reflection about the marketing. And it happens that in the EnSO use case, we did not meet a real interest for flexibility, so we decided to focus on more very thin glass and small solar cells, and keep flexibility on glass for maybe future developments.
Okay, very well. So this is mainly a question of reliability. The use case.
Yeah. The idea is really, we have at SOLEMS a very reliable process that's working on glass, and glass is cheap, very transparent, and very stable. So let's take this substrate, make it thinner, and obtain flexible cells. This is the challenge. And but there is still a lot to develop.
Mm-hmm. So we had this discussion before, but from your experience in energy harvesting and people trying to design system using energy harvesting, do they use just only one energy harvesting technique, or do they use also? Is it possible to use multiple sources of energy, like vibrations or temperature? What do you think? Is it a valuable strategy?
For my opinion, yes, it is possible to use several harvesting, and in EnSO we have several end users. I don't know if we can say the names of the companies. Yes, for instance, SKF is developing a solution for the trains to study the bearings and the evolution of the bearings. Maybe Janina can also comment on this because she is involved. We are sorry, we are developing a multi-source system for SKF in EnSO, where there are several harvesters all converging in the same battery. It is possible.
I see. Okay. Okay, thank you very much. Janina, for you, I have another question. I've seen that in your presentation, there's a maximum temperature of 140 degrees. Is that right?
Yes, that's right.
Yeah, and so what makes this limitation? What is the reason for the limitation, and what happens if we go beyond this temperature?
So it is possible to use also higher temperatures, because these are interesting applications, because there's much energy available. But in the EnSO project, the focus is on low temperature differences, and that's why we have to adapt our thermoelectric harvesting systems when we want to build them for other applications with higher temperature differences or with higher temperatures. For example, I mentioned that the internal interfaces can be soldered. And so we have to choose the right soldering process and the right materials, for example. But it is possible to build systems that can be used for higher temperatures, up to I think the maximum is 200 degrees, but it's the absolute maximum for our systems.
Okay. And beyond that, this is a question of the soldering that needs to evolve or find another way to maintain the components. But the material itself is still safe, right?
Yes, the material itself can be used for temperatures up to 200 degrees, for example. And what we have to adapt is are the materials around the thermoelectric active materials, the connections and all this.
And is it used to supplement an energy source like a primary battery, or is it used just as a 100% to deliver the energy to a system? What is the most common use case?
The most common, I think, both systems will be used. Some end user need an application that is that doesn't need a battery. Then it is a little bit more difficult to calculate everything, because sometimes the heat isn't always available. So it is not so easy to make a completely independent system, and a battery can help to overcome these difficulties, because it's like a buffer for the time when the heat is not available. But in general, both options are possible and are requested. So.
Okay, very well. Okay, and for you, Jérémie, my question would be the following. You mentioned a number of use cases where, but is it for the multiple use cases that you have shown? Is it the same harvester that you are using for every use cases, or did you design a specific harvester for each use case?
So when we receive a demand from the customer, we studied the use case itself, and depending on the use case, we have used several kind of energy harvesting source. So that's why we studied this different source. And for instance, we used our piezometric generator when it's possible because it's our own technology. But we have also used magnetic generators, for instance, in a bunch of projects, and it's working fine for specific applications as well when we have a quantity of movement which is higher. And we know, for instance, and this what I mentioned in my presentation as well, that electromagnetic generation based on a motor is also possible in use cases when we have high-speed movements. So we generally we only use one type of energy harvester. We don't combine several technologies for the same use for a cost point of view. But we are open in our developments to other technologies than the one we developed on our own.
One of the key aspects of your technology is that you can generate power even with very slow movements. Even with just a quarter of a turn, you can collect energy. Is that right?
Yeah, slow movements and small forces as well, because that's something I didn't mention. But our main market focus is ventilation. And in air pipes, the airflow is very low. You don't feel much the force of the ventilation when you are in a room. So therefore, you need tiny movements. The airflow is small, but that makes that, or let's say, our turbine turns with a very low torque. So it can be rotated with a low torque, and it's not possible with motor, for instance. So yeah, tiny movements, small speed and the small forces.
And a little bit like the question I asked to Janina, what would be, is there a kind of maximum speed or that you can achieve, or is it just a limitation of the mechanics of your system?
There is no max limit then. It can be used at high speed. The same system can go from very low speed to high speed. The only limit, let's say, if you know that your application has very high speed and it doesn't go to low speed, then that means our technology is not the one that is competitive in this use case. We know that for high speeds, for our high forces, we know the dynamo one. For instance, when you see the wind power plants, they are not made with our technology, and they are made with standard electromagnetic technology, because there you have a lot of quantity of movement, so high speed and high force as well.
Okay, very well. So now maybe a question for all of you. If I knock at the door of SOLEMS, MAHLE, or ENERBEE, and I want to start a project with you, I have a few ideas in mind, but we start from scratch. We have to design everything from scratch. Do you think that how long would it take to move to the first prototype? Is it a question of months or of years? So what is the typical timeline? So maybe Anne, you can reply to that.
Yes, yes. For SOLEMS, the requirement, if it's feasible, we make the study in a few days. see at least if the product can be made. And then if the prototype can be made, it takes a few weeks.
Okay, that's quite short then.
Yeah.
And for MAHLE, what is a typical development?
Well, I would say 2 to 3 months, perhaps. It depends on the application and on the size of the prototype. But I think this is possible because we have to calculate the application and get to know the heat source that is available. And after that, we can start ordering the material and building a first prototype.
Okay, okay. And for ENERBEE, same question?
Let's say our range of application is very wide. So if we take, for instance, ventilation prototypes that were used to do and produce, prototypes are available within a few weeks because that's something we used to manage. And but if we start from scratch with a very new use case, then I think it requires 3 to 6 months minima with a new use case in a new application. Because what ENERBEE does is not only the electricity generation, but we handle the sensor powering and the data transmission as well until the fulfillment of the end user application. So that let's say requires several steps and study, and the first one to study is the real use case.
Yeah, your business model allows a turnkey solution at the end. Okay.
Mm-hmm.
Okay, so thank you everyone for these very interesting presentations. So I would like to thank you again for your contributions to this first webinar, and I will take the opportunity to announce the next edition, the next webinar, which will be the number 2 in a series of 3. It will be on November the 8th at 1 p.m. again, and this time we will talk about the micro energy management. We are going to talk about storage and power conditioning. And we will have Mr. Raphael Salo from Seva Leti, who is also coordinator of the ENSO project, and Dr. Peter Spies from the Fraunhofer IIS, and he will make the presentation on the power conditioning itself. So to remain informed, so follow us on Twitter or on LinkedIn, and you will soon receive the link for your registration. But for now, I would like to thank again all the speakers, and I would like to wish you a very nice afternoon.